So I have a question for you to consider here that is going to require the cases method in order to solve. So how many 5-letter words can you make from the letters in success? So this is a sequence of letters question, so the order matters. Let me jot that down for you. Success has 7 letters in it, 1, 2, 3, 4, 5, 6, 7, but I'm only using 5 to make these letter sequences, so I'm leaving some behind. And if I look at that sequence of letters, I have a triple S and a double C. So there are some indistinguishable letters here. Pop that up there. And just to complete my set of core questions, there are no conditions on how to do this. So anytime that happens to you, where you end up with some objects being left behind and some indistinguishable objects, the technique for eliminating those overcountings conflict with each other. So in order to solve that problem, you have to use some other technique. So the issue here with this word is that I'm only trying to make 5-letter words. Some of them are indistinguishable. So I'm going to have to try and reduce this problem to either eliminate this issue or to eliminate this issue. So the technique I'm going to use for this one is to manually deal with some letters being left behind. Once I do that, I should be able to count the shufflings of the letters that I am taking and deal with the indistinguishable objects with our counting techniques. So to show you what I mean, if I were to do a 5-letter word out of these letters, I'm going to have to leave 2 letters out. So the first case number 1, that I'm going to consider is that you leave out 2 S's. Leave out an S and an S. So if I do that, that means that I'm going to be shuffling the U, the E, 2 C's, and 1 S. So now that I've decided that I'm leaving these 2 S's out of my shufflings, I have a smaller sub-problem to solve where I'm only shuffling a U, an E, an S, and 2 C's. Now if that's all I'm shuffling shuffling 5 out of 5 letters. So this is no longer an issue. In this sub-problem, I'm no longer having to deal with the fact that some of the letters are left behind. So I would count this by taking the 1, 2, 3, 4, 5 letters that are left and shuffling them, and I will have to eliminate the double counted C. Now 5 factorial is 120, 2 factorial is 2, for a total of 60 ways. So by manually leaving these letters out, I have reduced the problem down to 5 available letters to make 5-letter words from, and then I can just count them like I did in the last section of permutations. Well, that's all well and good, but this is not the only set of letters I could leave out, which is what ends up generating the rest of the cases I have to make. So instead of calling this case number 1, I'm just going to make a chart here of my possible cases. And they're going to be defined by which letters I choose to leave out. So if I left out an S and an S, I could also leave out an S and a C. in that case, I would be shuffling the U, the E, a C, and 2 S's. So that's going to look like 1, 2, 3, 4, 5 letters shuffled, and I have to eliminate a double S, which is another 60 ways I could do this. Next case I'm going to consider, in the right color, is if I left out an S and a U. So if I did that, I'd be shuffling the E, 2 C's, and 2 S's. So that case is going to look like 1, 2, 3, 4, 5 shuffled letters, get rid of a double C and a double S. So 5 factorial is 120, 2 factorial is 2, 2 factorial is 2, 120 divided by 2 is 60, divided by 2 is 30 ways that I could shuffle these. Next case, I'm going to shuffle the S, or sorry, I'm going to leave out the S and the E, which means I'm shuffling the U, 2 C's, and 2 S's, which means I have 5 factorial, shuffling the 1, 2, 3, 4, 5 letters, eliminating the double C and the double S, which gives me those 30 cases again. So I ditched an S, and an S, an S and a C, an S, a U, an S and an E. Those are all the combinations where I drop at least one S. So the next case I'm going to try is forcing myself to drop a double C. I'm going to run out of space there. If I drop a double C, I'm left shuffling a U, the E, no C's, and 3 S's, which would be 5 factorial for the 5 shuffled letters, and then I have to drop the triple S. 5 factorial is 120, 3 factorial is 6, 120 divided by 6 is 20 different ways. You can see I've run out of room on the board here. This exercise does get pretty tight after a while. So I'm going to erase this center part, and I'm going to push these numbers over just so I have some room. So at this theoretical pet store where there are 4 kittens, 5 puppies, and 3 birds, that's 4 and 5 is 9 and 3 is 12 animals available. And 11 people are taking animals. We'll get to that in a minute. But Kim hates cats. So in this particular example, the fact that Kim hates cats means that she either takes a puppy or she takes a bird. And so that's 2 different scenarios that this can play out. So this is an example of a question where the condition that was applied is what generates the cases. So those are easier to set up. Case number 1 would be Kim gets a puppy. And case number 2 would be Kim gets a bird. So, all right. Now if we do that, that means that instead of distributing 12 animals to 11 people, we're only distributing 11 animals to 10 people because Kim has already been allowed to pick and one of the animals has been chosen to go. So we're going to only be sorting, assigning 11 animals to 10 people. Now, for the purposes of this question, we're going to assume that all cats are the same, all puppies are the same, and 3 birds are the same. We could do this question 2 ways. In fact, maybe we'll do them both ways. The first one, I'm going to assume that all kittens are the same, all puppies are the same, and all birds are the same. So that means that I have indistinguishable animals, 4 kittens, 5 puppies, 3 birds. And I'm not taking all of them. I'm only taking 10 of those 11. So that in itself generates cases. So within these cases brought on by the condition, there are subcases based on which animal gets left behind. So try not to play Sarah McLachlan's song in your head when you think about this. But at the end of this exercise, if Kim gets a puppy, there may be a kitten left behind. So left behind. Or there might be a puppy left behind, or there might be a bird left behind. The same thing can happen if Kim takes a bird. The last animal left, all on its own at the pet store with no one to love it. See above regarding Sarah McLachlan songs. Kitten could be left behind, or that animal could be a puppy, or it could be a bird. So, if Kim has a puppy, and I'm just choosing people to take kittens, well, there are 10 kids left, and there are 4 kittens available. So I'm going to choose, oh, hold on. I would normally choose 4 people to take a kitten, but I've pre-decided that one gets left behind. So I'm only choosing 3 people to take a kitten. That means that there are 7 left who get to choose a puppy, and there are 2 left then. Oop, hold on. Kim has taken a puppy, so there's only 4 puppies left to choose from, which leaves 3 kids left who get stuck with birds. I mean, get to have birds. So lucky. In this case, where a puppy is left behind and Kim has taken a puppy, there are 4 kittens for those first 10 kids to choose from. The 6 that remain only have 3 puppies left to choose from, right? The puppy that Kim didn't take And so that one's gone, and this one is left behind. So there's only 3 that get chosen, leaving 3 kids stuck with 3 birds. If Kim gets a puppy and a bird gets left behind, then 4 kittens are assigned to 4 of the 10 kids. Of the 6 remaining, there are 4 puppies to choose from. And of the 2 remaining kids, they take 2 birds. The third one was that bird that got left behind. If we carry on with this little exercise, if Kim takes a bird and there's a kitten left behind, then out of those 10 people, we have to choose 3 to take a kitten, because 1 kitten gets left behind. The 7 children remaining get to choose from all 5 of the puppies, and the 2 kids remaining get stuck with the 2 birds. Why 2 birds? Well, there were 3 and Kim took 1, so there's only 2 left to go. If Kim takes a bird and it's a puppy that gets left behind, then we have to choose 4 of those 10 children to take a kitten. And then of the 6 kids remaining, we have to choose 4 to take a puppy, because this puppy gets left behind. And of the 2 remaining, they get a bird. And if Kim takes a bird and there's a bird left behind, then we choose 4 of those 10 kids to get the kittens, 5 of the 6 remaining to take a puppy, and the only kid that doesn't have an animal gets stuck with whatever bird Kim didn't take and whichever one didn't get left behind. So if we go through and we do all the NCRs for these, I did them in advance, so it's maybe going to be a bit faster. 10 choose 3 is 120. So I'm going to fill that in for every place where I've got a 10 choose 3. 10 choose 4 is 210. 7 choose 4 is 35. 6 choose 3 is 20. 6 choose 4 is 15. 6 choose 5 is 6. And 7 choose 5 is 21. Now the bit at the back where you only have 3 kids left and they have to take 3 birds, or there's only 2 kids left and there's only 2 birds, those are all trivial selections, so they're all 1. Just pop them in there for completion. So 120 times 35 is 4,200. 210 times 20 is 4,200. 210 multiplied by 15 is 3,150. 120 times 21 is 2,520. 210 times 15 is 3,150. And 210 times 6 is 1,260. So, since this is a cases question, and you can do it this way, or 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 this way, I need to add those all up. So 4,200 plus 4,200 plus 3,150 plus 2,520 plus 3,150 plus 1,260 gives me 18,480 ways. So if we treat each kitten as indistinguishable, each puppy is indistinguishable, and each bird as indistinguishable, then we'd have to set our cases up this way with subcases, and we'd end up with 18,480 ways. So if you think that each animal is unique, so and this is probably closer to the truth, that a black kitten, an orange kitten, a white kitten, and a tabby cat, you can tell them all apart. And so if I get the tabby cat, that's a different universe than if I get the orange one. So if that's the case, then I don't really care about which flavor of animals we get. Kim gets a puppy. If Kim gets a puppy, then one of these is missing. So there are 4, 8, there are only 11 animals, and 10 people. So of those 10 people, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 people and 11 animals. So I'm going to choose an animal here. That's 11 to choose from. The only one I can't pick is the puppy that Kim walked away with. Be 10 left here, and then 9, 8, 7, 6, 5, 4, 3, 2. Well, that's 11 factorial, leaving one animal behind. So that's fine. But if we're going to do that, if we're going to treat each animal individually, then you have to consider which puppy Kim walked away with. So it is possible that Kim walked away with the Labrador, or the Poodle, or the Afghan, or the Husky, or the Mutt. So there's 5 different ways that Kim could have done that. So I'm going to have to take this and multiply it by 5. So 11 factorial is an outrageously large number. 399,168,000 multiplied by 5 gives me 199,584,000. 199,584,000 different ways that could shake out. Now if Kim gets a bird, so we take a bird out of the list, that still means that there are 11 animals left to shuffle amongst 10 people, which means one of them gets left behind. But if we're going to treat the animals as distinct objects, then Kim could have taken the blue bird, the red bird, the green bird. Sorry, my bird knowledge is limited. But we're going to have to multiply this by 3. So 11 factorial multiplied by 3 gives me 119,750,400. $119,750,400. But since we could have done this with Kim getting a puppy or Kim getting a bird, I'm going to have to add them together. So 199,584,000 plus 119,750,400 gives me 319 million. That's going to go right in my face. 319,334,400 different ways. So by changing the assumptions on these questions, you can see that cases can be generated by having indistinguishable objects and leaving some behind. That's one way. Or, like this question, a condition can cause you to consider this scenario or this scenario, you add them together. Or the one we did in the middle there, where the condition has created 2 cases that you must consider, and within each of those cases there end up being sub-cases because there are indistinguishable objects and you're leaving some behind, as well as a condition you have to satisfy. So you should be able to go back to the permutation questions and the combinations questions from the last 2 pages, and you should be able to go back to the questions you identified as requiring cases to solve. And using these 3 questions as a model, see if you can tackle how to set up the cases and count them on your own.